recording. Okay, I will share my computer screen again. Okay, so for us to do any of the modeling, we firstly need to build in the geometry model. So as I mentioned that for excuse me. For our case, we focus on the computation. We do not focus on to have that in the pre-processor or that's in the post-processor. For the pre-processor, we using that in the open source of the software. And for the post-processor, we using the open source of the software as well. Okay, so for the pre-processor, using the open source of the software, so that will be a little bit more of the complicated. If you have that the access to the commercial of the software, like in the Abacus, then that will be great. Okay, so I will demonstrate. We have the building the geometric model and that's in the base model. So we were using the commercial of that software using the Abacus. So then after that, after we building that in the model, we transfer the Abacus in the input file. So then to convert to our software, then we given that in the material property, boundary condition, and the loading condition. So then we were using our software to do the calculation. So then where we were using the open source software like the ParaView to do that in the post-processing. Okay, so this is that's in the model. Okay, here this is not exactly follow the international standard. Actually, is follow that's the loading the experimental which we doing here at the University of Tasmania, the rock mechanics laboratory. So we did that in the sample. We have the diameter of the sample, which is 57.1 millimeters. So we know the standard one, which is 54 millimeter. Then you have the thickness should be equal to half of that in the diameter. Okay, it's around that's 25 or of that in the millimeter. Okay, we using that in the tetrahedron of that the element. Okay, we have 187 thousandths of that in the tetrahedral element. So between tetrahedral element, we were inserting the cohesive element. Okay, so we were using about 348 thousandths of the cohesive element. It's relatively is bigger of that in the cohesive element. Okay, so for this, I will not introducing that how do you build of this model in that in the Abacus, since I think that in the Abacus I have that in the good of the tutorial, it should be easy for you to build in this. Okay, so then I already building this model. So I have already prepared that in the input file. Okay, so I will show you. Okay, so now let's switch into my computing screen. I will switch into the Abacus. Okay, here this is that's in the Abacus and that's in my computer. So Abacus, you notice that actually for the student version, so that's free. But obviously for the student version, so they have some of the limitation. Okay, for the Abacus model, let me bring the pre-existing model. Okay, I goes into the file input. I already built in that model. Actually, what I prepare here, so that's the input file. So now then I goes into Abacus file input model. Okay, so I prepared that's in the BTS3D model of the here. Okay, then I click into this one. So then you can see that's in the model, so which will be open that's in the Abacus. So Abacus, has a very good of that in the visualization. Okay, so that's the model is like this. Okay, we have 3 of the parts inside here. So let me show you that in the 3 of the parts. Okay, the 3 parts we have that in the top of the loading plate. So you can see I can hide some of that. So we have that in the, okay, sorry, I have this, that's in the bottom of the loading plate. So the bottom loading plate, yeah, you can see here, this is that, yeah, follow, that's in the international standard. So you should have this in the curve, which should have a certain angle fitting the diameter of your sample. So then we have that in the top of the loading plate. Yeah, so then we have that in the rock of the samples in there. Okay, 3 pots. Okay, so for these 3 pots, yeah, obviously we have the loading plate. We were regarding that as the steer. And for the sample, we regarding that as the rock. So we needed to specify with the different of that the property. Okay, so firstly, let me show you that the input file, how that the input file looks like. So as I introduced last time, for HFDEM, the input file, so that's based on the optical input file. So, okay, so let me open that in the input file. Okay, I have that in the input file, which is prepared. That's here. Okay, this is that the input file, which we visualize that in HFD in opticals. Okay, opticals in the input file, which is looks like this. Okay, you can see here. So we have 3 parts: the top plate, the bottom plate, and that's the rocking sample. Okay, for each of the parts, so you need to have the node of that the information. Okay, here that's the first row, that's the node node. Then the secondly, sorry, the first column, then the second column is the coordinate, x coordinate, y coordinate, so z coordinate. Yeah, so for the 3-dimensional, any of that in the point, you need to have that in the 3 of the coordinate. Okay, then after that, so this is a list of that in the node. Okay, then we have that in the element. Okay, element here, we using that in the 3-dimensional element. Okay, if I draw that in a 3-dimensional of that in the tetrahedral element is like this. Okay, so you have that. A triangle. Okay, suppose I have here, this is that in the top of the point. Okay, this is that's a typical of tetrahedral element. So the tetrahedral element in opticals, which is called C3D4. Okay, so then you can see here, this is at least, okay, so the first column, so that's the element number. Okay, I suppose this element number, so that's number 1. So then I have that node number. So node, that's corresponding 4 of the nodes here. Okay, I suppose that I have this, the first node. So I have this 6,818. Okay, so here you have that in the rule. Then I have this node, which is 6,820. And then this one, which is 6,821. Okay, then I have here, this is that in 6,822. Okay, so this is that's what is the meaning. So you have that in the first column, which is represented the element node. Then the second column, which is represented the first node, and so on. Second node, third node, fourth node. Okay, so this is that's the data structure in Abacus. Okay, for our case, so we have that in the data structure, which is here. So which is exactly the same as that in the Abacus. Okay, so what we have here, we firstly have that, yeah, so the total number and that's the total nodes. Okay, here, this is that the same as the lost presentation. Okay, so let me show you that in the compounded presentation. Okay, here, what we have that's the data structure. Okay, so this is that I already showed that to you in Abacus. So that's when we have the border in Abacus, how that looks like. Okay, so here, this is that what I showed that in the our data of the structure. Okay, we have that 3 parts. Okay, before the 3 parts, we have that the total number of the elements, total number of that nodes. Okay, I will box that later. Okay, we have 3 parts. So 3 parts, which is here on that's the right hand side. So we have the part 1, that's the rock. The part 2, that's the top loading plate. The part 3, that's the bottom of the loading plate. So this is exactly the same as that for the 2-dimensional modeling I introduced before. Okay, so then what are we given that? We firstly given that is the total number of the nodes. Total number of the nodes, we needed to sum of that the elements and the nodes for each of the parts. We sum them together, so that's getting the total number of the element. And then on the right side, that's the total number of the nodes. So this is exactly the same as that for the 2-dimensional modeling. Okay, so then after that, we show the first part. Okay, the first part we have that's the rock. It does not matter which what that's the lane you given here. You can give that here called the rock, or called that's the rock specimen. Okay, then we have here that's the number of that's the elements and the number of that's nodes in this slide, in this part. Then after that, so we have that the horizontal of the translation, and that's the rotation. So that's follow what is that in Abacus. Okay, so then after that, so we have that the element. Here, this is that's the difference. First, to do the 2-dimensional modeling, so we specify that's the element, the type, so which is 1. So we using the triangle of that's the element for the 2-dimensional modeling. And for the 3-dimensional modeling, so we specify that's the element to the type, which is the H. Okay, H, which is corresponding, that's in the opticals, and that's in the element to the type. So which is C3D4. Okay, anyway, so that's the tetrahedral element. Okay, then we have the remaining of the data structure, which is follow what is in the opticals. So we have firstly, so that's the element to the number, then element to the no. Okay, then we have that in the 4 of the nodes. The nodes is no. Okay, that's the first section. So then we have here, we have besides the rock there, so we will have the top loading plate, and that's in the bottom of the loading plate. Okay, so here we have that's in the data structure, which is exactly the same. Yeah, so you notice here we recently, oh, let me come back. So we using that in the translation. So that means I have that in the top loading plate. So I have the top loading plate. Depends on how do you build that in the geometric border. So it's easy. So you have a small of the gaps there. So this small of the gap, there is no meaning for you to calculate that. You can place that initially So you make that the top plate and that the rock which is initially contacted with each other. So you can see here. So we actually, which is moving this. So moving this is the loading plate. So a very small of that along. So we have this that's in the x direction. So you have that in the y direction. So we move this a little bit up a little bit. That means initially when we constructing this model, actually we have a little bit overlap there. Okay, so for the top loading plate, or that's in the bottom of the loading plate, we have the data structure, which is the same. So as that's in the optical, so firstly, we have that's the element. So that's the node. Okay, so what we do, that's into here, yeah, is the same as what we introduced since last time. Okay, so what I do is that according to that in the opticals, I have that in how many of the nodes, then I copy this one. So then I paste that into here. So that's the load number. So then that's the element in the number. So I copy the maximum of that in the element number here. So then I paste in that into here. Okay, so remaining here, we have that in 0. Then for the element, so what we do is that we copy this part. Yeah, so here I have a huge of that in the number of the element. Yeah, so I would suggest you to install, yeah, a text of that in the code. Okay, so is that we copy this part. So you copy this part. Okay, so then you paste that. So you our code. So that's the element. Okay, then after that, so have that in the note. Okay, you notice that we in our course actually firstly presented the element information, then presented the sorry, in the our course is first presented the loading information, then presented the element. For our case, we first presented the element, then presented the node. Okay, yeah, so for the node, yeah, our course it's very good. Yeah, you can see using that and the star as the keyword. Yeah, so we open that in our software. We use this as the keywords as well. So then it's easy for you to look at that in the list of the keywords. Okay, then you copy the node of that in the information. Okay, so then that's to here. Okay, so this is that in the firstly of that in rock. Okay, then we look at that in the loading plate. So the loading plate, the top plate. So you can see is that's again that's the same. So what you copy is that the node of that the information. Here you do not have much of that in the nodes here. Okay, you copy this part, then you save that and paste in that to the top loading plate. So element the node. Then for the bottom loading plate, so that's the data of the structure is that's the same. Okay, then I skipping this one, so that's the same. Anyway, so what you do is that to copy that's the element and loading information from the outputs in the output file, yeah, to that's the data file which we are needing here. Okay, so this is that what we get in that, which is the Bayesian model. So after you have that in the Bayesian model, so you need to specify the initial of the condition. So we have that in the initial of the condition for us to do the resilience test. So what we were given that in the initial of the condition is like this. Okay, we given that in the initial condition, we have that in the top loading plate. We were given a velocity, or that's in the displacement. Okay, you have that in the displacement relevant to the time. Actually, is like giving a velocity. Okay, the bottom plate, we give that velocity. Okay, so to save the computational time, we give a velocity which is a little bit bigger. So we have that 0.05 meters per second. So which is much bigger than we use in the actual of the laboratory. We did the parametric analysis here. So if you look at our publication, so we did a parametric analysis. We say this one 0.05 meters per second. So that is corresponding to the quasi-static of the case. Yeah, obviously, so you have that loading speed, it should not be too fast. If you too fast, that will be the dynamic of the bleeding state instead of the static of the bleeding state. Okay, you will notice that later, if we have that the serious lecture, we have the time. So I will introduce that this to do the dynamic of the bleeding test for you as well. In that case, we will have an input bar. Okay, then we will have the rock samples here. Then after that here, we have a reflections bar. In the dynamic test, what you do is that you put in an impact on that the input bar. Okay, when you impact this, which we're introducing a stress wave, then the stress wave which will impact this. Okay, then in that case, you have this the dynamic modeling instead of that. For this case, what we introduced in here, so that's the static of the test. So I need to make sure I have this velocity which is small enough. Yeah, obviously, so it's impossible for me to make that the same as in the laboratory. I think that's in the laboratory, so which is all about that's 0.000. Yeah, so millimeter, that's per minute. So that's very small. It's unnecessary. As long as we have the loading region here, which is ensure that have the static achieving that the quasi-static, then that's sufficient. Okay, for this kind of that the boundary condition, and we actually needed to specify that material property as well. We needed for the circle of that in the spaceband, we will specify the property of the rock, and for the loading plate, we will specify that in the material property for the steel. Okay, what we do is that the remaining of that the data structure for the input file is that. Okay, so we have that in the structure here. First one, which is the velocity, initial. This means that's the initial velocity. You can see, so for all of that, the nodes are given that initial velocity, so that's 0. So that means initially they are static, they are not moved. Okay, you say, so we wanted to apply that in the loading plate. Okay, so this one, I'm not using that and given that the initial of the velocity. Instead, I will using that given a boundary of the condition. Yeah, I will given that here. Okay, I will introduce that later. Okay, so remaining of the structure, one of that is velocity, initial velocity. Actually, you have that everywhere, so that's 0. Okay, then we given that the element property. So for the element property, so we have, if we have that in the rock, you can see I label them as 0. If we have that in loading plate, I label them that as 1. Okay, 0 and 1. So which will correspond to later, which will correspond to, okay, if I goes into the next slide, so you will see what is that 0, 1 to represent it. Okay, 0 means that's the first of the column. So 1, so means that's the second of the column. Okay, then I will specify the physical mechanical property. So based on this label, okay, like that, if that's 0, so I specify, so that's the elastic modulus, and that's the Poisson's ratio. Okay, so here, this is that's the lambda, and that's the U. Yeah, according to elastic, if you know the elastic modulus and the Poisson's ratio, so you can calculate what is that in the lambda and the u. So that's the equation. So that can say that, and we have that in the u actually. So that's the shear modulus. Yeah, I think that's equal to E divided by 2 times of 1 and the Poisson's ratio, something like that. You can easily find that in the mechanics book to get into that. Okay, so that's what is that mean. Okay, so here I have that in the rock as specified that's in 0, loading plate as specified that 1. So then actually, so later I will give that in the different property. Okay, so then I have that in the loading property. Okay, so loading property is a USC. This is that we have a little bit different compared with the two-dimensional modeling. So for the two-dimensional modeling, I have that's an element property and the loading property. Actually, I mix them together. So I have that in the label, which is continuum. Okay, I have that in 0, then this is 1. Then for the two-dimensional modeling, I have this, and then this is 3, and then this is 4. For the three-dimensional modeling, we separated that. So we have that in the element property, the label, and the loading property, we separated that. So then that's why you see here. So for the rock, the loading property are still labeled then as 0. Okay, here, if I use that in different of the color, okay, I use that in yellow of the color. Okay, I label this as that in the all of that loading there as 0, then this is 1, and then this one, so that's 2. Yeah, so that's in the later. For this one, the rock specimen, so I keep in that and do not move. And for the top loading plate, I can add in that 0 0.05 meters per second of the loading velocity. And here I add in, yeah, although this is the value, that's exactly the same. But actually, so you notice that we have the coordinate here. This is different. Yeah, I have that's in the y coordinate point at the top. Then that's the x. Then in that case, actually, so for the top, I add in that in which way I needed to add in an elective 0.05, so that yeah, I can that making sure I have this moving that along that's elective 0.05, which means I letting this moving downward. So here I have that's positive 0.05. This is consistent with that's in the y-axis. So that's the moving that's in the upward. Then in that case, I'm loading that in the specimen. Okay, so as I mentioned that in here, for this part of that in the data structure, it will be difficult for you to prepare that by hand. Yeah, so I will share you with you, so that's a pre-processor of the program, a simple of that in C++ of the program. So I have that in prepared this in the program, so that's here. Okay, so let me, yeah, so I prepare that's in the, yeah, so this program, I will share that with you so that you can build any of that model. So last time we introduced that in, yeah, so for the two-dimensional BTS this time, so let me introduce that in for the three-dimensional BTS. So actually, so this is exactly the same of the code as that in the previous one. Yeah, only of that in the difference, what we use here is that I slightly modify that one, which is a cutter for the three-dimensional modeling. Okay, I will show you that what we using that here. Okay, I needed to use that in the Visual Studio. Let me open that in the Visual Studio. Okay, so the Visual Studio, so open that in the pre-processor. Okay, the computer is a little bit slow. Okay, this is that a very simple of the C++ of that program, or you can even call that C program. Okay, so last time I showed you that's this program. So this time, actually, I just slightly to modify this program, then I will generate that the data structure. So which I needed to use that for the 3 dimensions here. Okay, so you can see what I do that's here. Is related to that's the input file. Okay, so you can see what I given that. I say if you do the 2-dimensional body, you given that 0. If you do the 3-dimensional body, so you given that 1. Okay, we are doing the 3-dimensional body, so we given that 1. Then here, this is that's the total number of that's the element. So which is corresponding is the data file which you prepared here. Then that's the total number of the nodes which is correspond to that's here. Okay, so then the remaining this part you do not need to change that. Okay, so what you need to change is that's here. Okay, we notice that if we have that the element number, which is from 1 to 177484. Okay, we regard that as rock. So for the rock, as we say, we labeled that as that's 0. Okay, then yeah, I prepared an array. So if I have that the element number, which is smaller than this one, so then I give that label as that's as 0. Otherwise, I label that as 1. Okay, here, as I mentioned that last time, as starting is a little bit different for C. For the array, you always starting from 0. But in the abacus, yeah, so for the noding slow, so you always starting with 1. Okay, so that's 0 correspond to 1, 2 plus correspond to 1, and that's and so on. So that's why I just using smaller. I didn't use equals here. Okay, so that's through this sentence. So actually, so what you generate in that data structure, so you will be able to generate this part of that the data of the structure. Okay, so then let's come back into that one. Okay, let me clean my computer screen. Yeah, I need to put in this one here as well. Okay, so that's the animal property. So then the next one, so which is for the noding property. Okay, so this is that's you just need to use in this sentence you will generate data structures here. We can see if we have the node which is smaller than this one, so that's the node of the rock. Then in that case, so I given that label that's 0. So if we smaller than this one actually which is equal to that's the node of the rock, so which is this one, then add in the first of the loading plate. Okay, the first of the loading plate. So we look at that in the first of the loading plate. Yeah, the first loading plate, you have that in the loading number, so which is 1416. Okay, if you have smaller than this one, but it is bigger than this one, so that means you have this loading plate, the top loading plate. Otherwise, you have that in the second of that in the loading plate. Okay, so then this, which is specify the loading property. Okay, then the next one is to specify. Okay, so this part I firstly skipping this. Yeah, so then you can see through that and small of the a program, so we will be able to generate the data structures and that's here. Okay, then the next one is that we say initially, actually, we only have the contact that happens here, and the contact that happens here. There is no point for me to calculate the contact at the order of the location. Okay, so then I need to give you a series of the contact. Okay, what I do is that I do this through the abacus. So in the abacus, it's very convenient for you to define. Okay, in the abacus, I define the set. Okay, let me show you. So that's the settings here. So I define that in the settings here. So I have that in the bottom pledge. Okay, I have the bottom pledge. I make that initially that will have the contact. So then I have that in the top of the pledge. And so I will make that and have the initial of the contact. So that's easy. Okay, so for the rock, so I will specify. Okay, so let me show. Yeah, you can see here. Okay, let me remove that in the pledge, so that's easy for you to show that in here. So I remove the top pledge. So removing that in the bottom pledge. So then you see that's in the, yeah, you can see what I select. I just selected in that in the nodes at the top and the nodes at the bottom. So here actually it's very easy for you to select this. Okay, I can show you that in how I select that. Yeah, so I show that in the everything come back into here. Okay, since here, yeah, actually this is a two-dimensional problem. I only show that in the two-dimensional. Okay, you need to look in that and show that in the a perspective, non-perspective of that in the view. Okay, then I get rid of that in the top loading plate and that in the bottom loading plate. Yeah, so then I create a set. Okay, suppose I wanted to create a set. Yeah, I said that's the set of the three. When I create this set, so you can see that I can easily to select that anywhere. So what I do is that I select that which is close to the top of that the nodes there. You can click in the section for the nodes. You can click in that the section for the element as well. Okay, you can see here. So what I do is that I only select that at the top. That's in the set. It's very easy for you to use in the opcos to do that. So then you will have this kind of a set. Okay, so after that in the set, you can output in this in the create a job. So then you output in this data file. So you create a job. Yeah, then you output in the write in the input file. Okay, so after you write in the input file, so then what you get in that is here. Okay, so for this part, which were defined that's the set, this is that in the set which I defined there. I have that the top plate, I have that in the bottom plate, and that's in the top initial of the contact, and that's in bottom of the initial of the contact. So what I do that's here, why I need this kind of information. So I need this kind of information is that, okay, so let me show you that in the parallel view. Okay, so this is that's the result, calculated results in the parallel view. So if we go back into the initial of the step, so here, you will see here, so initially I have that contact. Yeah, I only calculated that in the contact. Yeah, at the top and at the bottom. And for the other location, I do not calculate the contact there. Since there, that will waste my calculations time, waste my calculations capacity. Okay, so what I do this so that in our code, so is through this, that's the data of the structure. Okay, so the data structure is here. Okay, we already showed that in how we generate the velocity, how we generate the element property, how we generate the learner property. Okay, then the later one is here. This actually is a flag. Okay, so for this, that's the rock sample. We have that's like this. For any of the nodes inside that, then I give that 0 since they won't have initial of the contact. Okay, for the nodes, if we have the nodes which is at the top or that's at the bottom, then I give that a flag which is equal to 1. So then, okay, so let me scroll down a little bit. You will see some, yeah, you can see here. So this is that's the flag. I given that 1, and then in the order of the location, I given that 0. Yeah, obviously, if you do this to prepare by hand, it will terrible. Okay, so what I do is that based on the abacus. Yeah, so using that in the abacus, let me clean my computer screen. Use the abacus, I can define this set. Okay, I copy this kind of a set. Okay, then I put in that into an input file. That's the input file. I copy that kind of information to put in that, and then I paste that into here. Okay, you can see here, this is exact the same. This is that. Okay, this is what it mean. We have that in the rock sample is like this. Okay, for the top plate, top part, we have this part initially, which will have the contact. So I have that's the top of the initial contact actually, which is the node no of that's the top. And here, that's the bottom of that's the inter contact. Yes, which is this part. So this is that's the a list of that's the node node correspond to this. Okay, here, this kind of data, which is automatically generated by the abacus. And if you are familiar with abacus, so you will notice that abacus is this data, which is very structured. So he will have each line, which will have 16 number. So after 16 number, he was starting as the next line. Okay, then for our case, what we need is that we needed to, okay, this one, you can give any of that the keywords. Yeah, convenient for you to remember, understand that. Okay, then here, this is that's the total number of the nodes here. It's easy for you to get that. Okay, so for example, if I wanted to calculate how many of that's the number of the nodes here, I only need to based on, okay, so I have that's the last row, I have that's 29. So minus the first row, that's 2. Yeah, then I plus 1 since I calculated the start line and the last line. Okay, then I have that 28 line. Each line I have 16 number. Then I multiply 16. But I have the last row. So I have this not full, which is missing some of the number. Okay, how many number we miss? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, then I minus 9. Sorry, so here. Yeah, I firstly need to make them. Then I click the minus 9, which is this one. Okay, so that's why I get this number, which is 493. Okay, then the remaining, that's the same. Okay, so then for the plate, so actually we included all of that in the element here. So here it's a little bit cumbersome. It's a little bit boring for you to list all of that numbers there. What I do, I just list the first element, the first node, the last node, then the step of the size. Then I will automatically to generate this. Okay, this is data which is what I will read. That's using. Okay, this is software. Okay, so using that's the small of the script. So which is here. I firstly given that all of that I given that a flag which is equal to 0. So that means that I do not have initial of the contact. Okay, so for the top, the node at the top, I wanted to have the initial contact. I read into this. Yeah, you can see I firstly reading this keyword, then I reading this one. Okay, so then after that, I reading each of that that. Yeah, I follow that in every line. That's 16 of that number. It's easy for you to program to do that. Okay, so after I reading that, since abacus starting from 1, I have here starting from 0. Then I minus 1. Okay, so then for that note, then I give a flag, I give that the 1. Then the corresponding, so this is that the structure is the same. I reading that in the second of this one. Okay, reading the third one. But the third one here, you need to be careful. So here, we reading that, we only reading that in the first one, last one, and then the step set. So I reading the first one, the last one, then the step set. Okay, so then, yeah, I generate that using a loop. Yeah, it's the loop from that's the first one, the last one, then the step. Then I can get in that the loading node. So after you get in the loading node here, you need to be careful. So in the opcos, each of the part, you have that the node number, which is always starting from 1, is a non sequence. But for our case, we have that sequence. Yeah, you can see I have that the rock, which is through 0 to this one. Then for the pledge, so this is the first one. I need to add in this number. And then this one, and that's why I add in here. Then for the second part, besides you adding that for the rock, you need to add in that for the first part as well. So then, which is 1. Okay, you give that in flag. Okay, so after you get into this, okay, then you run this is the program. Yeah, right. You can set the bracket pattern there. You can check what if that reading is correct. Okay, so let's look into that whether we have that reading that's correct. So you can see here we have that in the first one. We were reading the keywords, which is this one. Okay, if I put in that my mouse in here, so you will see. Yeah, so that's reading. Yeah, reading that rock top initial of that the contact. Okay, then the next one should reading a number. Yeah, it's a reading 439. So that's exactly 439. Then and so on. So it will reading that, which we're given that in flag. Okay, so then completed the that. So then that's remaining. That's an output. So output in that initial of the velocity. Output in that in the element property. So then the loading flag. Okay, so then using this program, so you will automatically to get this part. Okay, so which is this part of that data. Okay, this part, which is the initial velocity. Yeah, so then that's the element property. So then that's the loading property. Okay, so then that's the boundary of the property. So then you copy that to the input file. Okay, so this is what is that's the input file here. Okay, so let me come to that starting from the beginning. Okay, velocity, animal property, loading property, so boundary loading flag. Okay, this is what is generating using that in script. Okay, what we have that in here, which is corresponding. So we say we have that in the first column. Okay, this is for the rock, then the second column for the loading plate. Okay, then what are we given here? The property we given here, this is given that for the rock of the property. We given that the elastic borders, Poisson's ratio. Okay, so here this is the same as that for the two-dimensional modeling. Okay, so here we go through that in the lastly time. Then this time I will not go through that. Later, when we have the time, I will go through each of the parameter. Okay, anyway, so at this moment, what you understand here, this is given that material property for the rock. And here, this is given that material property for the steel. we know that in the steel, we have the elastic models, which is all about 200 gigapascal. So that's why I given that in 200 gigapascal right here. Okay, here actually I given that in multiple 10, 200 gigapascal multiple 10. That's for the contact. Okay, so here this is that I will not go through something that anyway. So that's the parameter. Okay, so this is that in the boundary condition. For this one, we quite simple. So we have that in the rock, we given that in 0, top loading plate given 1, bottom loading plate given 2. So you can see top loading plate are given nothing. The rock are given nothing, all of that in 0. And here for the top loading plate are given that in, which is let is moving down 0.005. The bottom loading plate are let is moving up, so that's in 0.005. So that's given the boundary condition. Okay, so besides that, we say we need to insert of the cohesive element. Okay, we say here this I draw a two-dimensional modeling. Two-dimensional is easy for you to understand that. So we have that in the triangle of that in the element. We insert of the cohesive element here. So this is that in the cohesive element. Okay, so the cohesive element, you need to define that material property. What we have defined is that define the cohesion, define the friction angle, define that the tension strength. Okay, so the other one is the parameter. Yeah, I will introduce that later. Okay, so for the cohesive element, how we insert in the cohesive element. So this, how we insert in the cohesive element, which is through this one. So you can see what we insert in the cohesive element. So we have that in the rock. We have the element loaded, element label. We label that's 0, 0. So between 0 and 0, so this one means this element, and here this means this element. Label between them, I insert a 0. Okay, so this 0, which is corresponding, I insert in the cohesive element. Okay, the cohesive element is so that's 0. Okay, 0. So this is rho, which is represented the property of the cohesive element. Okay, so then this is that's the input file. So after we prepare this input file, so then you will have the control file, which is exactly the same as that last time we do the two-dimensional modeling. Okay, so then what we do, okay, I already prepared that the input file, so which is here. So this is that's the input file. So then I copy this input file. So then goes into that's the have exe. I have this that's in the software that's here. Then I paste that in here. Okay, so then I can let that to do the calculation. Okay, so then after that, yeah, I run that in the code. Okay, so suppose I run that in the code. Okay, so then I give you a lane. Okay, I say that's the test is, you can give that any of that lane. Okay, I give that BTS3D. Okay, test. Yeah, I have already, yes, I had that the test 2 there. I given you another of that lane, test 3. Okay, then it was starting to compute. Okay, so after that in computing, that's finished. Yeah, actually, during of the computing, you can visualize of the results and say, okay, so compute. So then I visualizing the results using the parallel view. Okay, so I deleting that and everything in that in here. Okay, so then I have that in the parallel view. Okay, so this one is just we did that. So you can check in that in the results in here. Okay, from here, you can check in that in what you define that's in the material. No, yeah, so we have here this is 0. And here, so we given that the 1. Yeah, you can visualize in here. You can visualize that in initial of that in the contact in here. Okay, after that, the calculation is complete. So then you can visualize the calculations the results. So like in this one, I already had calculated the results. So that's the available here. Yeah, so here I show that what is okay. Let me show that in the stress of that in the distribution, vertical of that in the stress. Okay, so if I goes into that step by step, okay, so the last step, so this is that's the fail of that here. If I goes into in the middle of the steps, okay, 50, so you can see here only see the stress concentration. So if I go that's 100 of that steps, yeah, you see that's the crack is initiated here. So if I look at that at the bottom, at the end here, so you will see that's the crack. Okay, you can show that the, yeah, so here that's the vertical stress. So you can show that like the shear of that the stress. Shear stress actually is which will show that's very good of that the visualization since here. Yeah, you can see here that you will clearly see that split in that middle. Okay, you can show that the, so what is that the field of that the cohesive element there. So you can see here, okay, we show that the damage. So macro damage, at this moment you can see none of that the value, which is correspond to 1. So actually, what you have there only have that the macro of the damage. Then if we continue, like that show 100 steps in here, okay, you will see that's the macro damage, and you will see on a cracking that happens that in here. Okay, if we go into the next step, yeah, you can see that's the final of that failure. Here, you can filter. Okay, if I filter that, since macro damage actually is not really of that failure, you can see here that's the damage value, which is 2e minus 15, is very small of that value. Okay, I only show that really that's fail. Yeah, then I filter this one. So then you can see here, this is only show that they really have that field of that the cohesive element, which is exactly corresponding. So what is that's the length that's here. Okay, so this is that you can visualize various of the results here. Show that the different stress, the principal stress, the strain, yeah, so as well. Okay, I will not show that. Yeah, you need to learn that part view, yeah, to see how to look at that part view. Okay, the other thing is that besides we wanted to get in that in the failure, we wanted to get in the stress strain curve as well. Okay, for the stress strain curve, after the calculation, which we're generating a file, which is this one. So then after that, I copy this one. Yeah, so I copy this file to here. Yeah, then I use the Excel to open this file. Okay, so the Excel file, so open that, you will look like this. Okay, so after you have this Excel file, you can draw that the stress strain curve. Okay, suppose I draw this. Okay, what we have here, sorry, we have here, this actually is a vertical direction. Vertical direction, I have that's Y direction. Okay, so then I draw this, the stress strain curve. So then you will be able to get in that in the stress strain curve. Okay, so here, this is that in the, yeah, so perfectly that in the loading, then the plastic, then that's in peak, then the fail. Okay, then here, after that fail, since you have that continuous loading, you have the other part, which is the contact, so which where makes that the fold of that increase. Okay, so this is that what I put in that in the PowerPoint presentation. Okay, so let me come back into the PowerPoint presentation. Oh, sorry. So here, this is as a visual lessons result. So where is my PowerPoint presentation? Okay, so that's here. Okay, so this is that. Okay, so here I actually show that. So a part of view, you open that, so then you are getting the results, and so looks like this. Yeah, so then you are getting that in fail. So then getting the completely. So that's the stress strain curve. Yeah, so I have this all of that in the input file. I will send you this in the input file. This is to Tenshin. So then Tenshin, please share that in your group. Yeah, okay, so I will stop that here. Yeah, obviously I introduced a lot of things here. You will, it needed to you spend some of the time to digest this. I will provide you the software and will provide you the input file and provide you that the C++ script. So then you need to spend the time, yeah, to work on that. Yeah, so the first step is just to run the model, which I sent that to you. So then let you to be familiar with that. Then after that, you can build your own 3-dimensional of the BTS model. Yeah, okay, thanks everybody. Yeah, I stop in here, hand it to you, Professor Zhao.
Thank you, Professor Liu, for such a wonderful and detailed report. Professor Liu, I had 2 questions to ask. First, we know that PFC need to use the macroscope parameter to simulate macroscopic parameters. How to select mechanical parameters when using HFDEM to simulate in many engineering or other engineering?
Yeah.
Is HFDEM directly use the macro parameters or macro parameters?
Yeah, great. Yeah, thanks, Professor Zhao. That's a good of the question. Yeah, I think that, yeah, so when you build in that in the fractal, so actually you have this needed to select the macroscopic of the parameter instead of the parameter directly from the laboratory. So like that, if you use the PFC modeling, the first step, what you need to do is that do the unit-axis complex test and the bi-axis complex test. Yeah, so you calibrate what is the input parameter, then what is the output parameter. That's involving the very complicated process. Yeah, I think for our case, we have this is much simple compared with that HFDEM. Okay, maybe I use one of the our previous of the publication as an example to answer. Yeah, so Professor Zhou's the question. Okay, so let me share my computing screen. Let me using one of that in the publication. So we did that in the parametric analysis. Okay, so let me find that in the paper. Okay, the publication. Where is that in the publication? Okay, okay, I using a 3-dimensional of that in the paper. Okay, so this paper is that completed my PhD student. Yeah, so published that in the computational mechanics. Okay, so what the input parameter I show a table. So that's what is that the input parameters there. Okay, so we have that in the input parameter. I'm making that a little bit bigger. So the input parameter, yeah, should be somewhere around here.
Okay, I see.
Yeah. Yeah, so the input parameters are that's here. So we need to input in that in the density on the board, the person's ratio, tension strength, cohesion, internal frictions angle, mode 1 factor energy, mode 2 factor energy. And here, this is that's the, okay, so I would say I divided that into two groups. Okay, so this part, yeah, so that's the macroscoping of a parameter. Yeah, then the other part, so this part, yeah, so yeah, I can say this part of the parameter I can directly to determine from the rock mechanics laboratory. Yeah, for the rocket, so we have that the density. So here, what we building here, so this announced is a little bit larger than the number of the rock, and the elastic body to Poisson's ratio, the tension strength, and the cohesion, and the internal friction angle. Okay, so here this is that's exactly the same as that what we usually get from the rock mechanics laboratory. Yeah, but that's the order of the parameter. So here, that's the macroscopy of the parameter. Yeah, so for here, this, we do not have good of the best to determine that. For the Buddha one, actually, we have that in the formula. See, if we have the formula, this is actually replace that in G1. So this is related to the Buddha one of that in the fracture toughness. If we know that the fracture toughness, there is a formula, so I can calculate this one. But for the Buddha 2, actually, there is no formula to calculate this. Okay, the order of that in the parameter here, what we chosen that, actually, yeah, so this is that's in the contact. We chosen that in which is 10 times of that in the elastic body. You can see here, this is 12.2 GPa. So what we here, we multiply 10. And here, this is that's in the cohesive element. We say between of the triangle element, we insert in the cohesive element. But if that is fail not occur, you insert in the cohesive element should not affect the continuous of that in the behavior. So then we chosen here, that's actually, so that's the 100 times of that in the elastic borders. So this one, which is the 1,000th times, actually, so here, that's unnecessary. Yeah, we did that in the parametric analysis here. So you will notice that, yeah, for the, okay, so I'm making this a little bit smaller. Yeah, so then, yeah, if I wanted to build in this target behavior, so this is that's in the target behavior. Yeah, I did a series of the parametric analysis. Actually, you can see I only needed to have that 100 times. Yeah, so then that will be sufficient. I will build in that in the target of that in the behavior. Okay, so well, that's in other words, this is that's the numerical of the parameter. So this parameter, which is depends, which is adopted based on the laboratory of that parameter. And then here, that's the friction coefficient. Yeah, so this is that's the difficult to chosen as well. So what we have that's in the steel and the rock, which is the contact. The contact, if we have that in steel, usually we regard that quite smooth. Rock, we have that quite rough. If that's steel, the rock, we suppose that this surface which is a little bit that's smooth. If that's due to blocking of the rock, which is contacted that, so then this one, so we base on that residual of the friction angle when we have that in rock, when you have that in the failure, which is the fountain there. Then here, when we chosen this internal friction angle, this is actually which is chosen that in the peak of that in the friction angle. Yeah, since that's before of that failure, so that's the fail after that failure. Okay, here what are we chosen here actually, which is a tangent of that in the residual of that in the friction angles here. Yeah, it's true. Yeah, so for the input parameter, yeah, some of the parameter which you chosen that can directly to get that from the laboratory, while others, yeah, so the numerical parameter, so you need to choose that based on experience.
Okay, thank you very much. But another question is, what is the maximum number of elements in the case you use HFDEM to simulate what is the maximum numbers of the elements. In the case you have used.
Yeah, the number of that's the limitation. Actually, for our code, we do not have the limitation, which is limited by the hardware. I think that if you have good of that in the good hardware, so like that if you have A100, so for the 3-dimensional modeling, we use a few million of that in the elements. If that's for the low quality of that in the GPU, maybe won't be able to do the 3-dimensional modeling at all. Only be able to do that in the 2-dimensional modeling. So I can say, at this moment, for 3-dimensional modeling, we usually use a few million of that elements. So we haven't not done that using tens of millions or hundreds of millions or billion of that. We are working on if we, all of that in the modeling, which I showed here this moment, we are shown that on the personal of that computer or that's the HPC server only involving using one of that in the GPU. We are working on to using multiple of that in the GPU. We are like that, so I have a position in CSO. CSO is similar to Chinese Academy of the Science in China. So that's the research organization in Australia. So for their case, they have that. They have the HPC computer. They have 456 of that the GPU there. If in that case, so after we solve that into using multiple GPU, we can use billions of that in the elements.
GPU-parallelized HFDEM is a wonderful work. Recently, I used the BFT to simulate the forward stick sleep. One case I must use about 3 days to simulate one case. Okay.
That's great. So you may didn't attend our previous. So in my presentation, I showed that a slope, which is a completely process of the slope as well. Okay, so maybe I can quickly show that in the presentation. So that's made in some time ago. Okay, so let me show that. So maybe in that presentation. Okay, so let's look into that. So. So here that's how one of that show that in the slope and stability. You can see using the strength reductions method, how that's in the formation of the sleeping plane. After the formation of that in the sleeping plane, which show that in the collapse of the process. Compared with the linear equilibrium method or the finite method with the strength reduction, we can model the entire of the slope and instability of the process. I think this is that compared with all of that method, we have that advantages.
Okay, thank you very much for your answer. 同学们，你们还有啥问题吗？请机会难得啊。
No worry. I think that most of that the PhD students usually they are, and some of them are master students. They are share to ask any of that questions. According to the previous experience, usually is that the professors ask a question. I never see any of the students ask any of the questions yet.
青青，你有问题吗？
You're forcing TC to ask a question.
我没有什么问题。
Yeah, so Tintin, so have you checked that the calculation of the two-dimensional BTS in your computer?
Yes. 我昨天看了一下。
Yeah, I
对。
had a look. I think that's yeah, it's your GPU to do two-dimensional modeling. I think that's okay. Yeah, it just taking about 27 minutes to complete in the BTS test.
Yes.
Yeah, obviously, so that BTS test is two-dimensional, does not involve a lot of elements. Okay, so after the presentations today, yeah, so let's try three-dimensional BTS to see how long does it take us. So in your computer to do this three-dimensional model.
Professor Liu, okay. Good morning.
Okay.
Good, very good presentation, and thank you for your patience. And I want to ask you a question. That can you introduce me what's fundamentally different between your code and RPA code? Because I listening you have say a lot of the RPA code and your code. So may I know the fundamental difference between the RPA code and your code? Thank you.
Yeah. Yeah, so our code, so that's completely differently from so our FPA. So our FPA is that's based on the finite element method. So finite element method we know. So the finite element method you cannot deal with that after the fracture is formed. You want to be able to deal with that the interaction. So like for our case, we have the RFPA for us to build in the crack. So what we do is that we have that making the elastic modulus of the failed element becomes smaller. Yeah, then if you have that elastic modulus, so that's smaller, you can easily have that the cracking element have the deformation, which is like that the element does not exist there. But for the case, if we have that the fail, we have that the fragment, which is the interaction. Yeah, for our FPA, actually, we want to be able to model that the fragment, that's the interaction. We did that, yeah, I remember when I was developing our FPA, so in order to attack this problem, we modeled that called the recompaction behavior. So we mentioned that. So when we have this becomes a compression, then in that case, we increase the stiffness of the field of the element again. So making that to model that the after the fragment form that the contact. Yeah, for our case, we use HFDEM, so we can physically to model that problem. Since our FPA is we do not have deal with the contact. Actually, so our FPA for any of the case, you want to be able to deal with multiple of the parts. All of the case, you only have one part that's in our FPA. While we look into that, be able to model the Brazilian test. So for our case, actually, we excavated many of that element, making that element becomes that quite soft there. Yeah, so that's the approximation. Yeah, I think that's the fundamental of that difference is that the RFPA is based on the continuous method. It's good to model that before of that failure. So when you have that the failure form, we using the damage mechanics and using the erosions method can model somewhat of that the crack or crack propagation, but you want to be able to model that after the crack, which is formed, the separation of the process. Then after that, the separation, the torsion of the fracture, and that the fragment mock pain. But for the cases for the HFDEM, since we incorporate the discrete element, the contact there, so then we can deal with the completely the transition from the continuum to discontinuum. So even after that, the formation of that the discontinuum, So then we will be able to model that the separation, then the mocking, then the torsioning of the fraction, and then the mock padding of that the process. Yeah, I think that's the difference. Yeah, obviously, so I think that Professor Tang is pushing that into making that in RFPA, which is combined with Professor Shi's DDA. Yeah, when you work in that, the DDA so can be somewhat deal with that after the fracture, but even like that. So for the coupling of RFPA and the DDA is that so during the DDA stage, you only be able to model that the interaction when did be able to model the further of the fracture and that's the fragmentation. Yeah, so my conclusion is that so HFDEM actually, so that's completely differently from RFPA. So RFPA is good to model that before of the failure. After that failure, so HFDEM is much more versatile compared with RFPA. Yeah, back to you, Professor
Okay,
Joe.
thank you. Yeah, thank you. Very patient, very patient. And RPA is China, you know, FEDM or your code is now. So the first station, the DUT University. The second station, I think is very better is Northeast University. I think you announce your FEDM, your code in China's university. I think so.
Yeah, exactly. Yeah, I think that's yeah. So the presentation I made in that. Yeah, I think that's a better feel for the presentations. You know, is university introducing the HFDEM. The first one, I think maybe around the 2015. Yeah, at that time, I do not have the GPGPU-parallelizations yet. In 2018, I think that at that time, yeah, we justly developing that in the HFD actually, so it's not quite mature. I think at that time, most of that, what I bet in that is about the two-dimensional modeling. Yeah, then in 2019, I was attending an international educational conference, which was in Harbin. Yeah, so I bypassed to Shenyang. Yeah, so then I visited. Yeah, so Professor Yang. Professor Yang, actually, Professor Yang was not there. Yeah, so most of that is his PhD student. Yeah, Professor Yang was yes spent that in the holiday. Yeah, I think that yeah. So I wanted to talking to Mark and Professor Joe as well. I noticed that so now in China, so you have that. Yeah, it's good of that research funding. Yeah, I think that we can build a GPU server. Yeah, either in Northeast University or in Dalian University of the Technology. Yeah, so that kind of server, yeah, which will be using, we apply to using the state of the art of that in the GPU card. Yeah, and this moment actually, so in my hand, I have that in the state of the art of the GPU till the last year. Yeah, but in future, with the development of the GPUs, I think that we will have the new of that in the GPU, which will appear. Actually, this GPU, so now the state of the art of the GPU becomes much more and more that's the expensive. So if I have that a small of the group, I cannot afford that. Yeah, so if we have a big of that group, we apply that the funds from yeah, so the government, we can build in that in the comprehensive that's in the GPU platform. Yeah, so in Dalian University or that's Northeast University. So then in that case, we will be able to build in a comprehensive that's in the computational GMCAX group.
Okay, thank you, Professor Liu. And I noted that you 巴西 test， 哎，这个就是刘老师，您那个这个巴西的那个圆盘的那个实验呢，好像是我们用 RP 也做过啊，是吧？那个赵老师，我们好像是这个很多都做过，但是我看呢，它这个每个就是 different 的这个 code 呢，算出来这个 different result， 我就不知道这个是这个有限元、离散元，或者是这个非均匀性的这个原因呢，还是这个由于它那个端部的这个电板的刚度不同的这个原因？这个我就其实一直想问这个问题哈，所以我也看了很多这个 paper 也上这个写，就是这个您能不能给咱们这个解释一下，或者讲一讲？谢谢哈。
Yeah, so yeah, RFPA, so that's the basic of the rock mechanics experimental. I think that for any of that the in-house code or self-developed code, we always using that the precedence test, the UCS test, and do the benchmarking. Yeah, I think that's the reason why we develop an HFDEM. So we firstly do that in the benchmarking, and they for RFPA we do that in the benchmarking as well. And for the others, like now, yes, SPH, the smooth particle hydrodynamics, or that's the person working on the peridynamics PD. So they do this kind of that in the modeling as well. Okay, so I think that's yeah. So if I have that in my HFDEM, when did be able to build in the unit complexity? When did be able to build in the precedence state? Yeah, I one day I apply my code to start in any of that in the engineer problem. So I use this and that as a base. Yeah, for the different code, yeah, obviously we have that in the input parameter, which will be different. So like that, the two popular ones, so one of that in the PFC, so you will see the PFC have the input parameter and have that in the, what we get that from the laboratory for the precedence test. So you have that in the output parameter, input parameter, which will be completely that's the different. Yeah, so I would say so. This is definitely for the using the different code to build in the precedence test. So you will have that and some of that in the difference. But I think that to using that to calibrating the self-developed code like that in HFDEM, so I should be able to build in that in the essential of that in the information. So for example, yeah, I needed to get in that. I will have that in the crack, which will happen in that along that in the central line. Although that's exactly the crack initiation of that in the location. So I cannot say I will exactly initiate that in the middle of that in the breeding sample. Yeah, obviously for my modeling, which will influence by a number of that in the parameter as well. For example, for our case, we using that in the tetrahedral of that in the mesh, we insert in the cohesive element. So if I using that in perfectly a structure of the mesh, so I will get that in the exactly the same as that in the theoretical of that in the data. But for your case, if you use that in the unstructured of that in the mesh, so that's in the mesh which will have some of that in the influence as well. So I can show you one of that in the example. Yeah, so we show that. So what is that in the influence of that in the mesh? When we using the structured mesh, using the unstructured mesh, it's what is that in the difference? Okay, so let me show you that in one of the our paper. Yeah, so the publication. So, okay, so let's use this one. So we published that in the rock mechanism and the rock engineer. Yeah, as an example. Okay, so here, Yeah, so here this is that's the breeding test using two types of the different of the animals. You can see that's the right hand side using the completely that's the structure of the animal. Then in that case, I have that's the crack, which is exactly it happens that along the central line, and I have this surface so which is quite small of that surface. But if I use this unstructured mesh, so you will see this that's the zigzag of that's the shape. Yeah, obviously, yeah. So for our case, if we compare with the experimental results, so we would say the left side, which is more reasonable, and that's the right hand side, so is unreasonable. Since for the rock, we have that's heterogeneous of the rock. Yeah, I think that's the different code. Yeah, to get the different results. So that's due to that's the mesh or that's the particle, and introducing the various kind of the heterogeneity. But I think that's no matter. Yeah, so you have that's the small of that difference. That's understandable. That's reasonable. But for you, that's the BTS body quality of the BTS body. So you should capture that's the essential of that information. So like that, you have that the failure plane should be in the middle along the loading of the diameter, and you should have that the failure. So you do not have extensive of that the failure. Initially it appears that at the loading plate instead of that in the middle line of that the sample, and you should getting that in the stress strain curve. So like that's the breaching of that in the stress strain curve. Yeah. Okay. Yeah. So I'll stop that in here. So did I answer your question, Mark?
Oh no, yeah, very clearly.
Yeah, great.
Thank you, Professor Liu. 看看这个Dr. 国阳 and 这个郑虎有没有其他问题啊？看看其他同学有没有问题。啊，
刘老师，我这没有问题，刘老师。
Yeah,
没有问题，
great,
非常清楚啊，是这的，
Yeah. Noting that, yeah, so Jinghu and Guiyang, so yes, a previous presentation, I already asked a number of that question. Yeah, I think that's the next step. Yeah, so what we do is that we ask the postgraduate students to follow my tutorial. Okay, so I'm still recording. I think that